All right. Share. Oh, thinking about that. And here. Yeah. Yeah. That's awesome. Oh, all right. We go. Where did we leave off last time? Did we do example 2? We did example 2. Let's start here. Marginal productivity. All right, so I changed the due dates, all the homework and quizzes to final exam day. All right, so you can go back and keep working the homework. Right, that'll be a good way to prepare for the final. Right. Yeah, I have to have these due dates during the semester because otherwise students don't do their work. Right, they'll just procrastinate. But then again, it's like saying that you can't do the homework. That's kind of not the purpose in here. I mean, they have deadlines. So like in the real world, there's deadlines. If you're working at a company, right, you want to make money, there's deadlines. But the goal in here is for y'all to learn as much as possible. So if we have these deadlines we say, no, you can't do homework now, well, that just defeats the whole purpose of coming here to learn, right? So we have to constantly bluff all semester. Most of teaching is all bluffing, like your sign-in sheets, I throw those away as soon as I walk out of class, right? Like I'm going to sit there and read everybody's illegible signatures and go through some spreadsheet or something. It's nuts, right? All right, so here we go. Marginal productivity is the rate at which production changes for a unit change in investment. Thus, marginal productivity can be expressed as the first derivative of the function that gives production in terms of investment. So P here is productivity. Marginal means we're taking the derivative. All right, so obviously we're probably going to want to find out what P of X is, right? So we would integrate both sides. So move your dx over and integrate, and then you get this constant here, right? That's the general solution. We want the particular solution, which means we need to figure out what C is. Well, they tell us right here, what is this? When X is 3, they're telling us that P of 3 is 100, right? The process produces 100 units with the investment of $300,000. All right, so use this to figure out what C is. So set this equal to 100, replace X with 3, and you can solve for C. And this is the same stuff we've been doing from 13.1 to 13.5 or whatever. So there's nothing new here. Yeah, so you get 103. So that's what your C value is. They want to know if an investment is increased to 500,000, will you replace, this means X equals 5. You want to know what the productivity is when X is 5, plug in 5 into your productivity formula. You get 178 units. So an increase to 500,000 will increase production from 100 to 178. All good with that? Nothing new yet? Okay. Separation of variables. So this is cool. Get some new math here. And this is not complicated at all. So sometimes you start off with an equation like this. Y'all are used to dy dx equals, like that last one was like negative 6x. So you have y prime is a function of x. This has x's and y's and y primes. There's, a lot of stuff going on. And you can't really just solve the way we did it before, where we just did this, right? But what we can do is we can get all the y's on one side and all the x's on the other. All right. So for this example, we could move the y over and then the dx over, right? And then you can integrate both sides. They call it separation of variables. If you could separate the y's and the x's on separate sides sides of the equation, then you can still do your integrals. So that's all they're talking about here. It's called separation of variables. So here is an example. Get this point across. Down to here. So here is dy dx is a function of both x and y. So if we move our y's to the left-hand side and move our dx to the other, then we can integrate both sides. Y'all know how to integrate this and this, right? You would get this turns into this, and you have plus a constant. When you integrate this, you get this guy plus a constant. Move the constants and put them over together. A constant minus a constant is just a constant, so we just call that c, right? We don't need all these random constants. Collect them all and give it a name. C for constant. And at this point, because you have this y cubed and a y, you can't really rearrange this to be in functional form where it's y equals something with x's in it. So we just leave it like that, right? So this would be the general solution, right? We don't have any other information to figure out an exact value of c, so we just stop there. Yeah, here they say rename C1 minus C2, just call it C. And don't mess with it any further. You can't make that any prettier. Okay. And another example. Sales at a small store were initially $20,000. So sales at time 0 is 20,000 and have been continuously increasing at a rate of 5%. Okay. Y'all might recognize this formula. That's for, like, if you invest the principal, right, in the bank at an interest rate R over time T, that's the amount you get. That's your continuously compounding interest formula, right? Y'all know that one. Y'all use this lots, right? Okay. This is exactly the same thing, right? They're saying this is basically your principal, right? That's your initial amount, and then here would be your rate. So this is e to the 0.05 t, right? We could just write that down. But instead of doing that, let's back up a little bit. Let's set it up in a differential form. They're saying the change in y, right? So instead of a, they're calling it y here, right? Is 0.5. So the rate of increase is 5%. So take whatever you have and take 5% of that, and that's your rate of change. So that statement right there, that it's increasing at a rate of 5%, is exactly this. So instead of just going straight here, we'll take what they say literally and write that down, right? We only did this before because they told us that's the formula. Well, why is that the formula, right? Yeah. So if we start here, we can bring the y's over, bring the y down here, and bring the t over there, and then we can integrate both sides. The integral of 1 over y is natural log, and then the integral of dt is t. Bring the c's over here, right? Call this a constant. So we have what? Natural log of y equals 0.5 t plus some constant. At this point, we could get y by itself by doing e to the power of both sides. If you do that, those undo one another. And this plus c here, we could rewrite this as e to the c. Well, c is a constant, e is a constant. This is just a constant. I'll call it m. The book calls it m. Well, this looks exactly like A equals PE to the RT, doesn't it? But they call it M instead of P, right? Because this extends beyond finance, right? So they use generic letters here. So here's their version here, writing it all out nicely. Make this a little bigger. So yeah, you get the natural log. They throw an absolute value in there, right? But we're not thinking about negative values of y, right? What is our y? Our cell, we're not considering negative cells here. You can't take you can't take the log of a negative number, your calculator will choke, right? So they combine, we do the e to the both sides. This plus c is e to the c. Remember, if you have a like base, that's the same as adding their exponents. They call this m, and they put it up front. All right, and now to figure out what m is, we use what they told us. The initial, right here, the initial value is 20,000. So if you plug that in, set y equal to 20,000 and let x or t equal 0, e to the 0 is just 1. So this m is always your initial value. Okay, so then you could plug in your m as 20,000. Okay, so we already knew, again, we just wrote it down. We're like, oh, it's going to be 20,000 e to the e to the RT, right? Stop that, right? Y'all already knew this. Y'all could have just written this down, but instead we started off with this and we derived this formula. So what was the amount of cells after 4.5 years? Just plug in 4.5 in for t, all right? The next question is, instead of giving a time and figuring out what the amount is, they're going to give us an amount and ask us how long it'll take to get that amount. So we have y equals, what was it, 20,000 e to the 0.0, what was it, 5 or 4, 0.05 t. We derive that, they say, after how many years did cells reach 30,000? So you replace cells with 30,000, and we got to solve for t. So how do you do that? We'll divide both sides by 10 a whole bunch. So we have 3 halves, it's e to the 0.05 t. To get rid of the exponential here, let's take natural log of both sides. So those undo one another. And now divide both sides by 0.05. So that's what t is. That's all they're doing here, right? They replace y with 30,000 and then move this under there, which gives us 1.5. Take the natural log of both sides and then divide by that. That's it, right? Two variables, if they give you one, you can solve for the other. All right. When will cells be twice the initial value? This is interesting because it doesn't depend on what the initial value is. Just like with your investments, right? A equals PE to the RT, right? How long does it take to double your initial investment? If I replace the amount with twice the initial investment, the principal falls right out of the equation. The time it takes to double $1,000 is the same amount of time it takes to double $1. It doesn't depend on the initial investment, okay? So we use our formula, replace our y value with twice our initial value, the ends go away, right? Take natural log of both sides, so you have 0.5 t equals natural log of 2. Basically, the time it takes to triple your money is going to be natural log of 3 over the rate. The time it takes to quadruple your money is going to be a 4 there. The time it takes to have half of your money, if your money is decreasing instead of increasing, you're going to have a half there. do this. Suppose that cells, I'm going to use S for cells instead of the letter Y. All right. Time. They're currently $5,000, and they have a rate of 10%. Boom, y'all can just write that down. Y'all know how to do that. Of course, they want us to do it the long way, right? They want us to say, okay, the change in cells with respect to time is 10% of whatever the cells were, right? Like 10% of what the cells were, and that's the change in cells. All right, so then bring the S underneath, and then we have, bring the dt over there, integrate both sides. The integral of 1 over S is natural log of S. Integral of dt is t. Move this over here, and we'll call this m, or whatever. No, let's call it c. They call it c. It's still a constant. Do e to the power of both sides. So S is e to the 0.1 t times e to the c, and we'll call this m. So S is m e to the 0.1 t. We use the fact that S of 0 is 5,000. We have m e to the 0. So m is 5,000. So S is 5,000 e to the 0.1 t. What will it be in 4 years? Replace t with 4, right? When will cells double? Well, let's take the cells, replace it with 10,000, because that's double 5,000. We want to find what t is. It's over here. And this is just 2. So take the natural log of both sides. Those undo one another. So we have natural log of 2 equals 0.1 t. So t is natural log of 2 divided by 0.1. Exactly, we already knew that, right? The time it takes to double is natural log of 2 divided by your rate, just like the last example, okay? Now explain how exponential growth and decay functions presented in 4.2 were obtained. In the absence of inhibiting conditions, a population grows in such a way that the rate of change of the population is proportional to the population. The more people there are, the more people are having babies. So the rate of change is bigger for a bigger population. All right, that's what they're saying. The rate of change of population is proportional to the population. So here, P for population, right? And T for time. Why do they do that? dP dt equals KP, right? Or P dot is proportional to population. And that little alpha symbol, that means proportionality. Like for the ideal gas law, pressure times volume is proportional to temperature. So that's what that means. This is your proportionality constant. All right. They use the letter K constantly in all kinds of applications in physics. They use the letter K for the spring constant. Pretty much any constant, proportionality constant, they're going to use the letter K. So you can't be like, oh, that's the letter K. I know exactly what that is. It always depends on the context, but it's always the proportionality constant. But if we start off with this, here's the generic form. All right, they use Y's and X's to be as generic as possible, even though the example was talking about population. All right, but if you have this, you're going to bring the Y under here and bring the dx over there, and then you can integrate both sides, and you're always going to get a natural log. And over here you get a kx, and then you got a plus a constant. When you do the e to the both sides, you're going to get y equals e to the kx times e to the c. We call this m and put it out front. Call it whatever you want, but it's still that same formula that y'all have been using in finance for a long time. Okay, it's called the growth rate constant. See, usually like in finance, you use R. You use R always in finance, but otherwise you use K because R in finance is always an annual nominal rate, right? In finance, R is interest yearly. It's all based, the time is based in years, right? But in other examples, you might be considering rates of growth in days or weeks or months, right? So we use a different letter, we use K. And they use M here instead of P for principal. So M is the population at time 0, and a positive K value is growth. If it's a negative value, then it's decay. Look at mortality rate here. I wait to get out of here. I'm going shopping with my daughter. She has this little plastic shopping cart she pushes around with us, the HEB. Then at the end of the day, I have to take everything out of her cart, tell her she can't have it. That's the worst part. All right, the mortality rate for children under 5 in China, deaths of children under 5 years of age per 1,000 live births has been dropping since the start of the millennium at a continuous rate of approximately, I should use K, 8.3%. And since it's dropping, we need to have a minus sign there, right? Dropping, boom. In year 2000, so we're going to say the population, I don't want to use P here. What letter? They just use Y. Okay, fine. Y is going to be our population. At year 0 is going to be 37. Okay, so we could just automatically write down Y equals 37 e to the negative 0.083 t. At least they use t for time instead of x. We already know this. We could just write that down. Okay, of course, they want us to do it the long way. So we say, start off with their formula, integrate both sides, and solve for m. There's our formula, right? Let's see. How many years after the start, so t equals what, did it take for the child mortality rate to be cut in half? So replace y with half of your initial, all right? So plug that into your formula. We had y equals this, just replace y with 1/2 m. Notice the m's fall out. The time it takes for the population to get cut in half, or the death rate to get cut in half, doesn't depend on the initial death rate, okay? Take the natural log of both sides, so the e goes away, and then divide by 0.083. And don't worry, you're not going to get a negative time here because the natural log of 1/2 is a negative number. The negative cancel out. Okay. Log of anything between 0 and 1 is negative. After that, it's positive. So you get 0.84. Let's see here. If the model remains accurate, what will the mortality rate be in 2020? Well, this is t equals 20. Just plug 20 in for t. And there's a graph. You can see exponential decay. Look at another one here. Growth rate. Suppose an investment grew at a continuous rate from an initial deposit of $1,000. That's our principal, right? To the amount of 3,000 in 20 years. That's saying the amount in 20 years is 3,000. Okay, So we could say, since they already told us what P is, we have e to the RT. We need to figure out what R is. We can use this information to figure out what R is, right? This told us what P was. This is going to tell us what R is. All right, they call it, I'm going to call it A here. They call it K, I'm going to call it R, right? So we say Y equals, using their letters, all right? We're doing finance, we use amounts and principals and rates, right? But they're sticking with the generic form. So to use this to solve for R, well, you replace A with 3,000 and replace T with 20. Okay, so you can divide both sides by 1,000. So take the natural log of both sides. So K is going to be the natural log of 3 divided by 20. Plug that in your calculator. Oh, they use R. They call it K and then they call it R. Fine. K and R are the same thing. So here's the step-by-step of what I just did. Right? Plug in 3,020. Right? Divide by the 1,000. Reduce. Natural log of both sides. Divide by 20. So we have R is 5.49%. Limited growth. This is more closer to reality. So these exponential functions, like, yeah, you put money in the bank and it's going to like keep growing forever, right? But in the real world, it's not realistic, right? There's other factors, space restrictions or whatever, you know. You're running your business, it's like things start to wear out, fall apart. So these are good models for a certain amount of time, but eventually they might not be the best. So there's different variations we can do to our basic formula here. One of them is called limited growth. And this is what they do to fix it. So you think about population, like on the planet, they can't grow indefinitely. Eventually, there's not enough room for everybody, right? So there needs to be like a cap, right? So let's, they call it N. Let's assume there's a maximum growth, maximum population size, and we call it N. So if this is our population, we want it to cap out at N, all right? So what you do, instead of just doing KY here, you do N minus Y, right? So you can see that if Y is N, this is 0, so the change in population would be 0 whenever Y is equal to N, right? Y equals N tells us that the change is going to be 0. So we do the same thing we did before. Here's our basic setup. We can integrate both sides. If you move the N minus Y over here and the dx over there, you can integrate. This is going to give you natural log of N minus Y, but you're going to get a minus, right? Because the derivative of this would be 1 over that times the derivative of the stuff inside, which has a minus, so you need a minus there to cancel that out. And over here, you still got the kx, and we need to plus a constant. All right. Then you do the, let's move the minus over here. And this would be, we could still put plus c, because if you take the c and make it negative, we just rename negative cc, right? It's still a constant. Okay. And then you do your e to the both sides. So that goes away. So you got an N minus Y equals e to the negative kx, e to the c. We call this m, and we put it over here. So we have negative y equals negative m, negative n plus m e to the negative kx, multiplied by a minus, and then we have that. All right, so instead of just this, there's a minus here and a minus there. So we start off with the maximum, and then we subtract off something. So instead of looking at something that's growing like that, we start off with something like this and we subtract off something that looks like that. Okay, is what we're doing. So let's look at an example here. All right, researchers believe that a certain lake can support no more than 3,000 fish. So that's our cap, our maximum. There are approximately 50 fish in the lake at the present. So that tells us that M is 500. With a continuous annual growth rate, 0.25. All right, write and solve a differential equation for the rate of growth. So the change in population, k times n minus y, replace the n with the 3,000, all right, and the k with 0.25, and now we just need to integrate. So we move the y's to the left and the x's to the right. We want to integrate this. All right, so we're going to get the negative natural log of 3,000 minus y equals 0.25x plus some constant. Let's move the minus over. Negative. And it'd be minus c, but we're just going to call that c. Right? Rename it just like c1 minus c2. We just called it c. Right? A negative constant is still a constant. So we'll do e to the power of both sides. 3,000 minus y equals e to the negative 0.25x. E to the c, we'll call this m, but put it out front. We already know m is 500. Okay, so we have 3,000 minus y equals 500. Well, let's not plug it in yet. We'll solve for it, even though we already know that's what it is. If we get y by itself, we have 3,000 minus m e to the negative 0.25x. They said the initial was, what was it, 500 that was given? 500 fish at the present. So at present time is 500. So if you replace this with 500, that's m e. We have to replace x with 0. This is just 1. You can see here that m is going to be 3,000 minus 500, which is 2,500. So we couldn't just assume m was 500 anymore, right? That's what we wanted to do. But when we solve for it, it's something different because this is a different, this is limited growth. What this is the difference between the maximum and the present, right? So your m here is difference between max and present values, okay? Instead of just the present value. What did I do? All right, so here's the math we just did. They call it B instead of M. All right, so they use a different letter because they use M for present value. Since it's not the present value anymore, they just use a different letter. They find it's 2,500. So plug in your 2,500, and then we have our formula for, what is this, population. All right, we know what the K was, we know what the B is. So what would the population be in 4 years? Well, in 4 years, you just replace X with 4. Plug that into your calculator. How many years will And how many years will the population be? 2000? Just like the other examples, we had our formula, right? Y equals that. Just replace Y with 2000, and then you want to solve for X. So move the 3000 over, divide by the 2500, do the natural log of both sides, divide by the 0.25, and you get approximately 3.7 years. And that's it. Y'all have any questions? Don't want to work any homework problems or anything? You don't want to get out of here. I'll have, what, 13 minutes is my time. Do whatever you want with it. Any requests? Anybody out there in Zoom land? Any requests? Everybody wants to get out of here, right? Let's go. I'll have a good weekend. Monday we're doing Zoom, right? So don't come to class, Zoom in. Look in the announcements for the Zoom link, okay? I don't think the live sessions thing works. Should I do some quiz problems? I could do that. Let's look at the quiz problem. Let me see if I can figure out where they're at. Here. What is this, quiz number 7? I don't know. Let's see. The exam will be Wednesday, yes. So don't come to class, right? The exam will be Wednesday, all right? During class time, don't miss it. I don't want to have to grade a bunch of retests again. I hate that. So make sure you take the exam. I need to manage. Where is the quiz? Quiz 6? Is that the right one? Monday we will do the practice test. Yeah, the final is over everything for the whole semester. No problem, Randy. Approximate, right? Yeah. So the final will be, yeah, it'll be via MyMathLab, just like the exam. It'll be a MyMathLab final. Approximate the area under the graph and above the x-axis between. Use 4 rectangles. Okay, so they want us to do an approximation using rectangles here. E to the 2x minus 1/2. Let's graph this dude. Or was it E to the 2x minus 1/2? And where the from 0 to 2. Okay. Let's zoom in. Over here. This kind of okay. I'm going to. Dang it. 0 to 2. Getting closer here. 0. Come on now. 2. There. Zoom out a bit. Now we'll take a snapshot. Oop. They want us to have, and I need the numbers. One more time. 2. That. Four rectangles whose height is the upper left corner. Oh, so we need to take from 0 to 2 and divide it into four rectangles. So that means a width of what? A half. So right here at 0.5, we have, well, the first rectangle is going to be 0, right? The next one is going to be this rectangle, right? And then, because they wanted the left upper corner, so that one goes to 1.5. And then the last one, all right, so that's the approximation that they want you to do, right? So since the first one is at basically 0 here, right? Going through the origin, there's really just three rectangles we want to add up, right? So I'll call this one A1, right? A2, A3. So A1 is going to be f of 0.5 times 0.5, because the width here is 0.5, right? And the height is f of 0.15. A2 is going to be f of 1, that's the height there, f of 1, and the width again is 0.5. The third rectangle, the height here is, whatever that is, it's f of 1.5 times 0.5. So the total area, here's our function, right? We'd have, they're all times 0.5, right? So it's 0.5 times f, 0.5 plus f of 1 plus f of 1.5. So f of 0.5 is e to the 2 times 0.5 minus 0.05. Then we add to that e to the 2 times 1 minus 0.05. And then e to the 2 times 1.5 minus 0.05. Right? Put all those in your calculator and add it up, and you're going to get an answer. That's what they're wanting you to do here. Does that make sense? Yeah? Okay. So let's look. The following graph shows the average candy consumption of a town in thousands of pounds per year in selected years. Estimate the total candy consumption from 2002 to 2007 using rectangles of width 1 year and the height determined by the value of the function at the left endpoint. So what they want you to do is get the area of that, 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 the area of that. Oh, I went too far. When did it end? 2007. There. Find the area of all those rectangles and add them up, right? So since these are all a width of 1, basically the total here is going to be, what is this? 7 times 1 plus 8 times 1 plus 7 times 1, and then 6 times 1, 5 times 1. Oh, that's the last one. So just add those all up. That's the area of each of these rectangles. So in its approximation, right, because here it's too small, here it's too big, here it's too big, here it's too big. So it's going to be an over approximation, right? No, overestimate. This one. Use substitution formula to evaluate both these integrals. Okay, so the first, they're the same integral, right? It's just the bounds have changed. So the integral from 0 to 7, we would call this u to the 1/2, right? Where u is y plus 9, So du is the same as dy. So we could just replace dy here with du. The bounds are going to be different here. So this is when y equals 0 to y equals 7. But if we could integrate this, this would be u to the 3 halves, evaluated from y equals 0 to y equals 7. But u is y plus 9, 3 halves. Now I can just write 0 and 7 because it's assumed that if I don't write letters here, that it goes with this letter, right? So then we plug in 7 and plug in 0. So this is what, 2 to the 3 halves? No. 9 and 7 is 16 to the 3 halves minus 9 to the 3 halves. Let's see, 16 is 4 squared, right? And 9 is 3 squared. So this is 4 cubed minus 3 cubed, or 64 minus 27, whatever you subtract, right? We do this one the same way, okay? I mean, we could have done it differently. We could have used this and changed these bounds, right? I could have said, okay, if y is 0, then u is 9. So instead of saying y equals 0, I could have just said 9, because that was what u is. U would be 9 when y is 0. And I could have been like, okay, if y is 7, then u would be 16. I could have just put, you either put 9 and 16 because that's what goes with u, or you have to specifically say, I'm talking about y here, and then switch back to y and use the 0. So you can do it either way you want. We got 2 more minutes. We can do another one here. Mm-hmm. 6. All right. Is this the one where we type it into Mathematica? No. So Wolfram Alpha. Find the exact total area of the region bounded by the x-axis, the graph, and the interval from -1 to 2. X cubed minus 1. So you might want to graph this first. X cubed minus 1. Because you're tempted to just integrate it, right? I forgot, what was it? -2 to 1. So -2, 1. Uh, 2, 1. I'll try it out. So they want the area bounded right here. So here's -2, and here's 1. So we want this area in here, right? So because it's below the x-axis, if we integrate this guy, the integral of this is going to be a negative number, but they want the area. We better put a minus out there so that we get a number that's positive. Y'all remember that? All right, the area is below the x-axis. The integrals come out negative, but they're asking for the area. They're not asking you for the integral. So this would be negative x to the 4th over 4 minus x, evaluated from -1 to 2. So this would be negative x to the 4th over 4 plus x -1 to 2. So we have a negative 2 to the 4th over 4 plus 2 minus negative -1 to the 4th over 4 minus 1. So this is 2 squared, right? 2 to the fourth over 2 squared is 2 squared, which is 4. So I got a negative 4 plus 2. Minus 1 to the fourth is just 1. So this is negative 1/4 minus 1. Negative 4 plus 2 is a negative 2. Distribute this. This is plus a fourth plus 1. Negative 2 plus 1 is minus 1. Plus a fourth would be a negative 3/4. That ain't right. I should be getting a negative number. I screwed something up somewhere. We're going from minus. Yeah. Oh. I drew my picture wrong. We're going from minus 1 to 2. Yeah, I totally screwed this one. In my graph here, I read it backwards. Try this again. Here. Dang it. Yeah, this is all wrong. Don't do that. All right. Don't do that. We're going from minus 1 to 2. So we have to break this thing up into 2 different integrals, right? There's from minus 1 to 1, we're going to have to do the negative integral. What was it? It was x cubed. X cubed minus 1. So from minus 1 to 1, we want the negative of that because it's below the x-axis. And then we need to add to that the integral from 1 to 2, because that's going to give us a positive value. So that's our area, okay? So just like the rest of the math we just did, this would be a negative x to the fourth over 4 minus x, evaluated from minus 1 to 1. And over here we have x to the fourth over 4 minus x, evaluated from 1 to 2. So this is negative x to the fourth over 4 minus plus x minus 1 to 1. This is over here going to be 2 to the fourth over 4 minus 2 minus 1 to the fourth over 4 minus 1. So we would have, let's see, negative 1 to the fourth over 4 plus 1 minus negative 1 to the fourth over 4 minus 1. And this was 2, this is 4 minus 2 minus a fourth plus 1. So this is just negative 1/4 plus 1. Negative 1 to the fourth is 1. Negative is plus. Minus makes a plus. 4 minus 2 is 2. 1 minus a fourth is 3/4. Those can go away. 1 and 2 makes 4, plus the third gives us 4 3/4. That's my answer. I'll stick it to it. But you see, the whole point of this problem is the setup here. This is below the x-axis, so that's the negative integral. This one's above the axis, so that's the positive integral, and you have to add those together. So you have to break this into 2 parts to get the area. If you just integrate from here to here, it's going to take that area and subtract off this area, which is not what you want. All right. Yeah, no problem. All right, let's get out of here. Have a good weekend, y'all.